Great. Thank you very much. And I have the pleasure to move on with an industrial collaboration. It's a collaboration between EPFL and Swiss Grid. And welcome Professor Paolone on stage. He's heading the Distributed Electrical System Laboratory. And we have today online our colleague Asja, head of the network modeling and analysis at Swiss Grid. So I think this collaboration, to my opinion, is something which has a strong impact on all of us, and maybe we do not expect. And maybe Mario, you want to start to explain what it is about.
The presentation I'm going to give you now, with 4 hands with Asja, is about some of the problems that we try to solve in the most critical infrastructure we have in our modern society, namely the power grid. As you know, this is a machine that has millions of state variables. So it's not a robot that has some limited degree of freedom. We're talking about a system that is probably the most complex machine that engineers have ever built. And what we are trying to do is to decarbonize the way we are producing electricity from a situation where we have the majority of the electricity produced by controllable resources, to a situation in 2050 where the majority of the resources are stochastic and non-controllable. And the problem is how to fix the continuous balance that we need into the power grid. Well, I remind you that in power systems, you have the need of continuously balancing the electricity produced and consumed, because the energy storage you can have in the electrical circuits is extremely small. So typically, when you have a transient or a lack of equilibrium in your system, you have the transient you see on the figure on the top left. This is the frequency of the system. The frequency is a sort of proxy indicator of the existence of an equilibrium in your power grid. Now, when you have a disturbance occurring in your system, there are some counterbalancing forces to keep your system in equilibrium. In the very first instances is the inertial response of your spinning masses, and then what we call reserves. So essentially the valves that you are opening to your hydro turbines, your gas turbines, and whatever. And they're acting at different time scales. And the problem is that these kind of transients, when you have a standard power grid with spinning generators and standard powerhouses, may last in a critical condition several minutes. If you look at this transient in the Australian blackout that happened in 2016, it took 700 milliseconds. And the problem is to develop wide area control and protection systems that can counter-react with these timescales. Now, the problem is that if you look at the fundamental functions, automation functions that you have into the power grid, and you locate them as a function of the reporting rate, essentially how many information you are processing per second, and as a function of the latency that this application may require, you have the top left functions in this figure that are the standard control functions having in the control centers, and then those that are the most time critical on the bottom right of this figure that are protections. And you see that the most time critical ones, they need to act in hundreds of milliseconds with reporting rates of 50 or 60 informations per second. The problem is also that if you wanted to take robust decisions, you have to process information of a system that has a size of a continent. We're talking about the continental Europe power grid. So how do we solve the problem? Essentially, you're measuring information that in the electrical world are phasors. So essentially, from time domain waveforms, you're extracting complex numbers. And the problem is that we have to time align these information by using time dissemination technologies. And we are generally using time information provided by satellites systems like GPS, GLONASS, and Galileo to align the phases of this information and time tag them. Now, this kind of technology was also developed by my laboratory. It was one of the pioneering laboratories in this specific domain to essentially have solutions that can provide state estimation functions, wide area protection, and centralized control, irrespectively of the function that you're trying to implement. So essentially, we're trying to solve all the problems associated to these functions I was locating in this map by using a single infrastructure. And what we are trying to do is to transfer this know-how to SwissGrid in their operation, and leave the floor to Asja to showcase what they are doing in the control center in Aarau.
Thank you very much, Mario. Thank you very much, everybody, for the interest. So SwissGrid has since about 20 years, a wide area monitoring system where we collect about more than 20 PMUs from several countries in continental Europe. And you can see here on the slide the list of the countries where we collect measurements. And the last one is also Ukraine, because SwissGrid, thanks to this wide area monitoring system, is one of the responsible companies that has allowed the interconnection of the Ukrainian system to our continental European grid. What we do at SwissGrid with those measurements, we permanently, in an online way, assess the oscillatory stability monitoring on the system by checking if there are some power oscillation or if there are critical voltage phase angle differences across the system. And we also use them to check some post-event analysis. In the bottom of this graph, I would just like to show you what is the difference between traditional SCADA measurements that we have in control rooms and those provided by wide area monitoring system, where you can see that in the traditional way, we wouldn't have been able to detect that there was an oscillation ongoing in the system. Next slide, please, Mario. Why are we doing this? Is it really our concern? Well, it is. Just a few years ago, in 2021, was a critical year for the continental European grid, where we assisted to 2 system splits. Probably you as final users haven't noticed that, but we had our system that was split into 2 regions, a main grid still pulsating at about 50 hertz, and an island that was completely detached, that was going at its own frequency. Fortunately, we were able to re-establish the situation within less than a few hours. This is why network restoration, so how to restore a grid after a severe blackout, is becoming very interesting for all transmission system operators in Europe, including SwissGrid. And this is where the EPFL SwissGrid Framework Agreement actually starts, with the first research question: how can we restore the grid? The main challenge is that we miss still high-resolution data and models in order to model our grids from the dynamic point of view. I heard talking about models quite a lot today, but in power grids, that's still something that we are developing. And if you do the next animation, Mario, in this framework agreement between SwissGrid and EPFL, we are trying to develop methods where, based on measurements, we can detect and assess what are the actual models behind those measurements via system identification technologies. And we have identified wide area monitoring through phasor measurement units as one of the technological solutions that can enable us to do so. And that's all. I would just like to leave you with some takeaways. We talked a lot about the grid of the future, but the important thing that we have to already engineer about the grid of the future is how we are going to measure and sense the situational awareness of the grid. And only by using good time dissemination technologies like those provided by phasor measurement unit can we do that, especially thinking of a grid of the future where stochastic power generation is progressively being deployed in the grids. Wide area monitoring systems have already been embedded into traditional control rooms. So SwissGrid is only one of the 7 TSOs across continental Europe that has already an up and running wide area monitoring system. And the vision of the agreement that we have together with EPFL is to use synchronized sensing technologies also to enhance the resilience of the system, not only during normal state, but especially during critical operational conditions like those after a system split and potentially also after a blackout. And the final takeaway, I would like to thank you very much for having me online. I was not able to participate due to family reasons. So thank you very much for the organizers and for the audience for having me online today.
Thank you, Asja.
Thank you, Asja. I have a question. We have some more time. I have a question. You were talking about a framework agreement between EPFL and SwissGrid. when I hear there's a lot of interaction happening between EPFL and Swissgrid, and this is surely not a result of a one-year research. There's more behind. Can you explain a bit how the journey started and how it evolved?
Well, there is a strong link between the EPFL and Swissgrid in many forms. So we started many years ago with the establishment of the Swiss Competence Centers for Energy Research, where Swissgrid was a strong partner. I was the chair of the SCCR on power systems. And from there, we started a collaboration that was about tech transfer, was about hosting talented students. Many of our students are now engineers in Swissgrid, PhDs. Asja was a PhD in my laboratory and now is responsible of one of the most critical groups in Swissgrid. And now we are moving towards new challenges related to the change of the operational paradigms in their grid, and our partnership relies on what we had in the past and what we can bring to them in terms of know-how that we have.
So I heard it was about more than 5 years of a relationship, right? Between
Always even more than that.
Even more. So do you think this is key for this kind of systemic changes where you have a big impact and you have to also implement the element Swissgrid? What is key in this? Is this a trust? Is the person? Is a combination?
That's a good question, and I will also ask you to ask about that. But give me my opinion. We're talking about decarbonizing a system that took several generations of engineers to be built, and we want to do it in a decade or so. So I remind you that the power industry is an extremely conservative industry for obvious reasons. Therefore, convincing them about the goodness of a technology requires several rigorous stages that are beyond the simple mutual trust. There have to be in place processes to validate all these technologies. Asja, let you comment on what I'm saying.
Yes, Mario, definitely. I think that long-lasting mutual trust is the key for this kind of collaborations. We know that when we think about EPFL, we can find a serious partner that does not only fundamental research, but applied research, whose results can be seen and grasped in the medium term. And this, for us, is the key of this kind of collaborations. Results that we can see and that we can transfer to the industry with solid recommendations.
Thank you. So in the name from EPFL, thank you very much for this feedback. Highly appreciate it. Thank you, Asja. And I think we have to stop here today.
Thank you, Robert.
Thank you, Asja, for participating, for being online. Thank you both for coming on stage.